on with chapter 15. Here, quartz is often called silica. These are silica-based minerals. They're amethyst. The colors arise from putting certain elements mixed into this crystal structure here. We have aluminum metal. We looked at this general properties of crystals. Now we're here at energy and changes of state. All right, so we're going to do some calculations here with some of these. And so how much energy is needed to vaporize 180 grams of liquid?
Professor, can you go back so I can write the stuff down?
Yeah, which one?
That.
Well, I'm going to write these equations on the board. Change of state, which we call phase change. Q is equal to the amount of heat or energy that you need to either input or extract from this is equal to the amount times delta H of the phase change. And so we have another number of them. The amount need not be in grams, like they did the amount in mass. So Q is equal to the amount, the mass times delta H. But it depends on the units of delta H. You know, oftentimes delta H is given in units of kilojoules per mole. If it's given in kilojoules per mole, then we need the amount in moles. Or we need to be able to convert the amount into moles. So this is the equation that I use for the change of state. What types of changes of state do we have? We have delta H of vaporization, which is pretty much boiling or evaporating it. We have delta H of condensation, which is the reverse. And so sometimes what people will do is they'll just put a negative. A negative doesn't mean it's necessarily exothermic or endothermic. Negative just means it's the opposite sign. Whatever sign delta H of vaporization is, condensation will be equal, but just the opposite. And so if vaporization requires energy, then condensation is going to require removal of energy. And so we have vaporization, and then we have a couple of more. We have fusion. We call it just FUS, fusion, delta H of fusion versus delta H of freezing. Fusion is melting, freezing is freezing. Fusion and freezing. I don't know why they didn't call it just melting. It would be good if they just called it melting. There are others, you know, but I don't think we need to get into the others. Others would be sublimation, etc. And so that's the equation for whenever we have a change of state. Is that okay? Did you get it, Aaron?
Yeah.
All right. Now, we did this calculation the other day. So if you know 1 gram requires 1.13 kilojoules, then 188 grams will just require 188 times that. So the grams cancel out here. If this were kilojoules per mole, then we convert grams into moles and then cancel out the moles. So we'd use some dimensional analysis for this particular one. 212. Okay, this is the exact same equation here. Q, whenever we have a phase change, Q is equal to the amount times delta H of the phase change. Q is equal to the amount times delta H of the phase change. So this is fusion. Fusion's melting. Then we have solidification. Solidification is freezing. And so heat of solidification is heat of freezing, delta H of freezing, which is the negative of fusion. How much energy is it required to melt 25.0 grams of ice at 0 degrees C? So we need the delta H of fusion. I know the amount. The amount's 25 grams. So what is delta H of fusion for ice? So we go back and look it up. Let me go back into the table and see if they give it to us. So here I have H2O. Melting point is 0 degrees C, so we expect to melt. The heat of fusion is here. The heat of fusion is 333 joules per gram. 333 joules per gram. It's heat of fusion. So this is what's required. So 25 grams. We want the energy. Q is equal to the amount times delta H of fusion. So the amount is 25 grams times delta H of fusion. That's going to require 8,330, or 8.33 times 10 to the third joules of heat are going to be required to melt 25 grams of ice. When we melt that ice, what are we doing without all that energy? When you melt ice, the weird thing happens. Does the temperature change? When you melt ice, does the temperature change? When you heat things up, temperature changes, right? When we add heat. But did you know when we melt ice, it doesn't warm up? Why? We're adding heat. We're going to add 8,330 joules or 8.33 kilojoules. If we add 8.33 kilojoules, shouldn't it get hot? And so let's see what happens when we melt ice. Last simulation. So let me pull this up here. So ice. This is going to be molecular dynamics. Melting ice. Molecular dynamics is quantum mechanical simulations. What's happening? So it doesn't get hot. The weird thing is okay, ice has a very open structure. This is why ice is less dense than water. Here, let me back it up. And so it's a crystalline structure, but the thing is, this is not at ice at 0 Kelvin. There would be no movement. There would be no vibration. So what we have here are vibrations. We don't have rotation. We have vibrations. Ice has this very open structure like this. That is to maximize these. Do you see the dotted interaction right there? Do you know what we call those dotted interactions there? Those are the forces that hold water molecules together. What's the primary force that holds water molecules together called? It's a dipole, but it's an unusually strong dipole. The unusually strong dipole happens when hydrogen's bonded to fluorine, nitrogen, and oxygen, the three most electronegative elements on the periodic table: fluorine, oxygen, nitrogen. So this is an unusually strong dipole. It's called hydrogen bonding. And so it's primarily hydrogen bonding, and then we have some London forces, which are pretty weak because water doesn't have very many electrons. And so it's primarily hydrogen bonding. Well, to maximize the hydrogen bonding, the water molecules want to orient perfectly. So this hydrogen orients with this water, and this oxygen orients with that water. And so they're perfectly aligned to maximize that hydrogen bonding. And so what happens is it adopts a very open structure. There's a lot of empty space here. And so ice is not as dense as water. Water is more dense because all those interactions have not been minimized. You'll see it here. So this is what happens when we melt. When we add energy in the form of heat here, it vibrates more and more until we break that perfect crystal of ice there. And now we have liquid water. Liquid water, the energetics of the hydrogen bond aren't perfectly maximized, and there's a lot more kinetic energy, so it's difficult. Now we're going to vaporize. When we vaporize it, now you're separating it. And so we went from solid, liquid to gas. Even in the gaseous state, there could be some interactions here, but mostly they're pretty far from each other. In the liquid state, they're still touching each other, so there's still better hydrogen bonding interactions there. This is an open ice network here. This is freezing. This is the reverse. This is molecular dynamics. You can see the hydrogen bonding interactions there, forming and breaking, forming and breaking. Hydrogen bonding interactions are important. Hydrogen bonding interactions are largely responsible for the double helix of DNA. To maximize the hydrogen bonding. And so here we're doing the reverse. Now we've got to remove energy because there's too much kinetic energy. The water molecules are too excited, so we've got to cool down, get them to. So we're removing energy, but the freezing happens at 0. So that was the molecular dynamics of that. Let me just take a quick side peek at the double helix H bonding. There's a really interesting simulation where you turn off the hydrogen bonding and the double helix falls apart. I guess was it posted? It was not posted. Okay. Well, I'll look it up. But what's happening is all that energy is used to break the hydrogen bonding, the ones that are holding the ice crystal together, but not completely. They aren't completely broken because this goes into liquid state, so there's still hydrogen bonding interactions there. So that happens at 0 degrees C. There's no temperature change even though we're adding heat. The same thing goes for boiling water. Let me backtrack a little bit. When we boil water, the temperature doesn't change. Boiling water, what's the temperature of boiling water? 100 degrees C. Even if you add more and more heat, does the temperature change? No, as you add more and more heat, the temperature stays the same. What's happening is all that heat is going into breaking the hydrogen bonds and vaporizing the water molecules completely apart. All right. What happens though if we're not at the melting point or the boiling point? What happens is this. This change of state is phase change. This is a process. Versus an object. And so what I mean by a process is this melting occurring or boiling occurring, something like that. An object would be just like water, a glass of water at 25 degrees C. And so when we heat an object, what happens? Heat or cool an object, what happens? When we heat or cool an object, what happens is the temperature changes. Temperature changes. When we heat or cool a process, the temperature doesn't change. You just get more of it. And so as we add or remove heat, temperature does not change. Whereas when we add or remove heat to an object, the temperature does change. And so if we're dealing with an object, I'll cue the object, this is going to equal the amount times C times delta T is going to be a temperature change. This would be a process, Q, a process. And so this is what we got going here. Well, all people can say Q is equal to MC delta T. Amount times C times delta T. I don't write M because it doesn't have to be in grams. It could be amount in any units you want, pounds, whatever. Because C has different units, but probably easiest is to remember MC delta T. So let's just remember MC delta T, where M is the mass. So what is C then? C is called the specific heat. C is, well, actually C is the heat capacity. It depends on the unit. If the units are either energy is going to be in joules or calories. Per gram degree C, then we call that specific heat. C equals specific heat. If the units are in other units like joules per mole or something like that, then we call it molar heat capacity, etc. So we're just going to focus on specific heats here. So let's take a look at the specific heat and what the number means. So let's look at the highest and lowest number here. What's the highest specific heat you see?
Every number there.
Out of every number, which one's the biggest?
Water.
Water is big. What does that mean? That means that water can absorb a lot of heat without changing its temperature much. You know, have you tried to boil water? It takes a long time, right? And water has a high specific heat, meaning it can absorb a lot of heat without much change in temperature. What has low specific heat? Lead and gold are tied. They aren't really tied. They're tied at 2 sig figs. One's going to be a winner. Probably gold. 2 more sig figs. You know, if we went 3 sig figs, then they're different.
Solid gold.
Probably solid gold. Solid gold doesn't have a very high specific heat. What that means is that it's going to get very hot very fast. You know, if you add a little bit of heat to gold, it's going to get hot quickly. Versus water, if you add a little bit of heat to water, it's a heat sink or heat reservoir. It doesn't get hot quickly. And so the specific heat tells us, what impact heat has on temperature. So water is a good heat sink. Is gold a good heat sink? No, gold is a bad heat sink. Gold's going to get very hot. And so this is why if you have gold cookware, it's probably pretty good because the gold will rapidly heat up, Versus copper. Where's copper? Copper is going to take, let's say, about 3 times as much heat to warm up by the same amount. And so let's say gold takes this much heat to get to this temperature. Copper is going to take 3 times the amount to get to the same temperature. And so if you could, how much energy is required to change the temperature of 25 grams of water from 10 degrees C to 50 degrees C? Well, how do we know? Water in the previous example was a process, but now in this example, it's an object. How do we know if it's a process or an object? How we know if it's a process or an object is by looking at the temperature. Between 10 degrees and 50 degrees, is there any phase change for water? No. Whereas if we go back to the previous example, here, we're at 0 degrees C. If we add heat to ice at 0 degrees C, the only thing that's going to happen is it's going to melt. Right? And so here water is a process because of the temperature. 0 and the other temperature would be 100. At 100 degrees C, it's going to be a process. But water in between 0 and 100, or below 0 and above 100, will be a object. And so there's no phase change here. And so what's going to happen in this case is how much energy is required to change the temperature of water. So Q is equal to the amount, M times C times delta T. C is the specific heat. And so the amount of water we have is 25.0 grams. The specific heat of water, a lot of people have it memorized. You know how a lot of people have it memorized? Because do you know what the definition of a calorie is? Let me talk about the definition of a calorie first. One calorie is the amount of energy, or heat, the amount of energy required to warm 1 gram of water by 1 degree C. So if you take a gram of water and want to raise its temperature by 1 degree C, it'll take 1 calorie. That's the definition. Actually, the definition only holds, I think, between 4.5 and 5.5 degrees C, where water is the most dense. And then it varies, but it varies so little that we just say it's over a wider range. Well, do you know how many joules it takes to do the same thing? It takes 4.18 joules. And so we get this, 1 calorie is equal to 4.184 joules. That's how many joules it takes to do the same thing. And so a lot of people have the specific heat of water memorized because it's 4.184 joules per gram degree C, or 1 calorie per gram degree C. If we want the energy in calories, we would just use 1 calorie per gram degree C. But normally we don't work with calories. Normally we'll work with joules. And so the delta T, what is delta T? Delta T is T final minus T initial. Well, T final is 50 degrees C. T initial is 10 degrees C. So the total temperature change is plus 40 degrees C. So we got to heat it up by 40 degrees. So let's go ahead and do the calculation here. The calculation is going to be 25 times 4.184 times 40. So it's going to be 4,184 joules, or 4.18, so 4 kilojoules. If I did that correctly. Let's check the calculations there. Actually, I shouldn't go 4.18. Over wider temperature range, it should just be 3 sig-figs. I'm overstepping if I'm going 4 sig-figs. So we got 4.18 kilojoules. This is also in table 15.5. 4.18 was the highest. Remember? It was the highest value that we saw in that table. Table 15.5 here. The highest specific heat was for liquid water, 4.18 joules per gram degree C. This is the unit. Joules per gram degree C. All right, now we're going to do, what happens if we go and change the temperature and we have a change of state? And so this is change in temperature plus change in state. solid will warm to its melting point. Solid will change to a liquid at the melting point. Liquid will warm to its boiling point. Liquid will change to a gas at the boiling point. Gas will become hotter. We could summarize this in a diagram like this. This is what's happening. This is called a temperature versus heat graph. So we put the temperature on the y-axis and the amount of heat we're adding on the x-axis. So we add more and more heat as we go across here. So let's redraw this for us here. We're going to do ice. We're going to do water. So for water, we need two temperatures to keep in mind. We need the melting point, which is 0 degrees C, and we need the boiling point, which is 100 degrees C. And here we're going to have, melting occur and boiling occur. Between those temperatures, we're going to have a object. And so what we'll do is here, we're going to put 0 degrees here and 100 degrees here. 0 degrees C, 100 degrees C. And so let's start off with ice below 0 degrees C. If I have a block of ice at a temperature less than 0 degrees C, what's going to happen? If I have a block of ice at, let's say, minus 15 degrees C, if I heat that up, will it melt immediately? No. If I heat it up, so this is what's going to happen. As I add heat, the block of ice is going to warm up until it hits 0 degrees C. And so this is step one here. Step one is object. I have a block of ice, it's cold. I'm going to warm it up. And so Q1 is equal to the amount times what? Well, if it's an object, it's going to be the amount times, or I should just say, yeah, C delta T. It's going to warm up to 0 degrees C, and then once I hit 0 degrees C, if I continue to add heat, it's not going to warm up. You know what's going to happen? All that heat is going into melting. And so in 1, we have ice warms to 0 degrees C. In 2, we're going to have ice melts at 0 degrees C. And so Q2, the heat is not going into warming it up, the heat is going into melting it. So Q is equal to what? The amount times delta H of, what's melting called? Fusion. So the ice melts at 0 degrees C, and so all that heat goes into melting until we've melted all of it. Once all the ice is melted, then all ice has melted into H2O liquid. And so we no longer have any ice to melt. And therefore, all that heat's going into H2O liquid. Well, what's going to happen to H2O liquid if we add heat to it? It's going to warm up, And so in 2, water warms. We actually have to add a lot of heat. Water warms. And so this is an object. So here, this is object for 1, and then we hit a process for 2, and now we're back to an object for 3. And so Q3 here is equal to the amount times what? I just want the equation. And, yeah, amount times C times delta T, MC delta T. Until we hit 100. Once we hit 100 degrees C, then it's going to stop warming up. In fact, when water hits 100 degrees C, then it's going to start to boil. And so we'll say water boils at 100 degrees C. So this will be 4. 4 is boiling, which is a process. And the equation for this will be Q, what is it? Q4, Q for step 4 is going to equal the amount times delta H of vaporization. No, there's no delta T here. There's no delta T because the temperature doesn't change in a process. The temperature remains fixed. And then once I boil, there's no more liquid left, so all water has boiled. So all water has boiled. Then I just have steam. And if I add heat to steam, I'm going to get superheated steam. So, in other words, steam gets hot. Steam gets hotter. Gets hotter. Steam is already very hot, so I didn't want to use steam warms. Steam gets hotter. This is 4. So we could have superheated steam. You know, so as high as the temperatures we want. Continue heating it up. So Q for this is equal to the amount times what? Q4. This is Q5, sorry. Q5 is equal to amount times
C
times delta T. So this is what they're doing with this graph. As we add heat, since we're dealing with object, process, object, the equation changes. If the equation changes, then what we have to do is we have to add the heat for each segment. We don't have one equation for both processes and objects. We have separate equations for processes and objects. And so what we have to do is, to get the total, we'll have to just have a running tab, that is, just keep adding on. And it depends on where we start. We don't have to start here, we can start anywhere and end anywhere here. If we go in the reverse direction, then, going in the reverse direction, it's not, gets hotter, it cools, steam cools, so we hit 100. And then rather than vaporization, it's what we call condensation. So once all the steam is condensed, then the liquid water cools as we remove heat. And so it's the exact same equation here. Just the delta T is going to be a different direction, and we're going to get negative heat rather than positive heat. Negative heat means you have to remove it. Then we go here, and delta, when we cool the liquid water, it's going to freeze at 0 degrees. And so rather than delta H of fusion, we call it delta H of freezing or delta H of solidification. Our book calls it solidification. Then once all of it's solidified or frozen, once all of it's frozen, then we cool by removing more heat. And so it goes both ways. We only drew it the blue way, but there's the red way here as well. The equations are the same, if I just call this phase. What's gonna do is it's gonna be positive Q. Q will be greater than 0 this way, and it'll be negative going this way, but the amounts will be the same. No. If we do sublimation, then we have a jump. For sublimation, we jump from solid to gas, and so when we sublime things, we skip the liquid phase entirely. So, actually, let's make that here. Sublimation is giving me a temperature at which we go straight from solid to gas. We skip the liquid. This is called delta H of sublimation. And then the reverse process is when we go from a gas back down to a solid. This is called delta H, deposition. So we're depositing the gas as a solid, so deposition. This is why I don't really like the word solidification, because solidification, deposition are too close. So I'd like freezing better. And freeze is what they call it here, but they call it solidification up here. All right, so we use a graph like this to figure out where we're at. And so let's calculate the total heat transfer when 19.6 grams of ice initially at minus 12 degrees C is heated to steam at 115 degrees C. So we're going to take ice at minus 12 degrees C and go to steam at 115 degrees C here. And so that means we're going to go through all the steps, because we're taking ice at below zero, to warm it up, then melt it, then warm up the water, then boil the water, and then warm up the steam. So we're going to go through all the steps. So as we go through all the steps, then what we'll need is, we'll need all the numbers. We'll need all the numbers from the table 15.5. So let's go back to 15.5 and take a look at the numbers that we'll need here. Actually, we're going to need more. 15.5 doesn't have the days. These are all objects. Objects, heating and cooling, that's specific heat. So if we have ice, ice needs 2.06 joules to warm up a gram. Water needs about double that. Water has a much higher specific heat or heat capacity than ice. Steam needs about half. Water is the biggest heat sink. Okay, for the other one, we'll need this. These are for phase changes here. So we have heat of fusion and heat of vaporization. Fusion, melting, vaporization, boiling. And so we'll need the temperatures. For water, 0 and 100 degrees. 0, we'll have melting, 333 joules per gram. At 100 degrees C, we'll have boiling, which is 2.26 kilojoules per gram. Boiling water takes a heck of a lot more energy. When we melt water, we still retain the hydrogen bonding interaction. When we boil water, we completely destroy the hydrogen bonding interaction. So it's going to take a huge amount of energy. Look at this. This is 333. This is 2,260 joules. So boiling takes up a lot of energy here. And so ice melting, this is kind of short. But boiling, a lot of heat is required. Boil. So we need these numbers here. All right, so let's do Q1, which would be ice warms. Okay, so ice warms is objects. So let's go back to the other table here. Ice warms to 0 degrees C. So Q1, ice warms. So we're going to go from minus 12 degrees C to 0 degrees C. All right, so it's an object warming. Q is equal to the amount times C times delta T. So the amount is, I didn't write it down, I think grams of ice. 19.6.
Yeah,
19.6 grams of ice. The C, so we need the specific heat of ice. Solid ice is 2.06. So the units are going to be 2.06 joules per gram degrees C. So grams cancel. So the only thing we need to cancel is degrees C. And so the degrees C is going to be delta T, which is T final minus T initial. T final is 0 degrees C. T initial is minus 12 degrees C. So that's going to be plus 12 degrees C. So we're warming this up by plus 12 degrees. And so it's going to be 19.6 times 2.06 times 12. So that gives me 400. So Q1 here is 484.5 joules. And so the amount of heat required to warm this is 481.4 joules. Warm that. So our first leg here, 481 joules heat required. Okay, so for Q2, we're going to boil 19.6 grams, or not boil, melt. So Q2, we're going to melt.
Professor, would it not be 484.5 joules per degree C?
No, the degree C cancels too.
Oh, yeah, but you're right.
So we're just left with joules here. So we're going to melt 19.6 grams of ice at 0 degrees C. Okay, so the melting, how much heat is that going to take? Well, yeah, it's going to.
Sorry. Under there, you wrote 41.4.
Oh, here, yeah, I don't know why I did that. 484. 484, I'm going to carry an extra digit. 484.5 joules. I don't know what I was thinking. All right, so Q2, in order to melt ice, that's a process. So it's going to equal the amount times delta H of, what's the process? Fusion. So I need delta H of fusion. So I go back to the table and look it up. You don't have to have any of these numbers memorized. Fusion is melting 333. So the amount is 19.6 grams. And delta H of fusion is 333 joules per gram. So the grams cancel out, leaves me with joules. So let's go 19.6 times 333 equals 6,526.8 joules. So it didn't take that much. It took about 500 joules to warm up the ice, minus 12. But to melt it, we have to break the hydrogen bonding interactions, the perfectly aligned hydrogen bond. There's still hydrogen bonding interactions there, but we go from perfect alignment to not so perfect in the liquid. No, the liquid is much more random. And so in this second step, it's going to require 6,526.8 joules of energy to melt the ice. So in the third step, what are we doing?
41.
Yeah. So step 3, water. Warm. So we've melted all the ice. Now we just have water. We're adding heat. So water warms from 0 degrees C to 100 degrees C. That would be the max. So 19.6 grams of water warms. So how much heat is required? Actually, a lot of heat is required to do this. We're going all the way from 0 to 100 degrees C. And so Q3 is going to equal
MC delta T.
yeah, MC delta T. Or MC delta T. MC delta T, if you remember, is MC delta T. So we need a specific heat to see. A lot of people, like I said, have this one memorized for water. It's an important number. So 19.6 grams. C is, you see it? 4.18 joules per gram degrees C. Delta T is T final minus T initial. T final is going to be 100 degrees C. We don't have to use Kelvin for this. T initial is 0 degrees C, fortunately. temperature change is plus 100 degrees C, so we're increasing the temperature of the water by plus 100 degrees C. So that's 19.6 times 4.18 times 100. It's going to give me 8,192.8 joules. So warming the water costs a lot of energy. 8,192.8 joules. Once all the water's been warmed up, then we're at step 4, which is the water is going to start to vaporize as well. 4. The 19.6 grams of H2O liquid boils at 100 degrees C. So this is a process. So Q4 is equal to the amount times, process is vaporization. Heat of vaporization, or delta H sub vap. So we need to flip back to the other table. The other table is here. You guys know the number? 2.26. Yeah, 2.26. I know this number, but I know it in kilojoules per mole. 44.0 kilojoules per mole. They usually do it in the amount of moles, but it doesn't matter. In grams, I have 19.6 grams, 2.26 kilojoules per gram. And so the grams cancel. Let's see what that gives me here. So 19.6 times 2.26. 44.296 kilojoules. But I want to be consistent here because all these are in joules. Joules. So I'm going to convert this into joules. So this will be 44,296 joules. So to boil the water here, this is going to take up some time because it requires a lot of heat to boil the water. And so the actual, I didn't draw this to scale. If I drew this to scale, this would be the longest. We have to continue to add lots and lots of heat. So this is 44,296 joules worth of heat that we're adding to this. So by far the most heat is going to be step 4 so far. Step 5, well, it makes sense because here we have to completely kind of obliterate the hydrogen bonding between the water molecules. So the hydrogen bonding is really favorable because it's an unusually strong dipole interaction. In steam, there's minimal hydrogen bonding interaction in the water molecules. And so here on step 5, the steam warms. Steam warms from 100 degrees C to 115 degrees C. So we have 19.6 grams of steam warms. And so we're just heating an object. So Q is just going to equal the amount times, or MC delta T. Amount MC delta T, MC delta T. The amount is 19.6 grams. C, I have to go back to the other table. Maybe you remember it. 2.00. If I flip back to the other table, I'll take a look at it. It's 2.00 joules per gram degrees C times delta T. Delta T is T final minus T initial. T final is 115 degrees C. T initial is 100 degrees C. So we're warming up the water by plus 15 degrees C. So this is 19.6 times 2 times 15 580.0 joules. And so this last leg only requires 588 joules. And so what we need to do is we need to total up the energy here. And so I'm going to take 588 plus the 44,296 plus the 8,192.8 plus the 6,526.8 plus the 484.5. That gives me 60,000. So Q total is equal to the sum of the Q's. So I just add up all the Q's and I get 60,088 joules, or 60.0. Actually, I think I'm allowed 60.08 kilojoules, or 60.1 kilojoules cool energy. So let's see what they got here. So they generated a graph like ours here. Solid warms, solid melts, liquid warms, liquid boils, steam warms. Solid warms, 0.48 kilojoules. They did it in kilojoules, everything. So they go through all the steps here, and then we end up with the sum, which is 60.1 kilojoules. We add it while we're doing. All right, any questions on this? All right, this is the end of chapter 15, but let me just do a quick summary. When we heat an object, usually you just get more kinetic energy, vibrations, this type of stuff. Versus when we heat for phase change, when we do a phase change, you're breaking something or you're forming something. You're breaking hydrogen bonds, you're forming hydrogen bonds. So the energy is being used to do different things. The delta H's, the heat and all that depends on the structure, the crystal structure. When we think about gold, gold, what can gold do? A solid crystal of gold, the gold atoms can vibrate back and forth. Maybe what we could do is, even though it takes some time, this didn't work so well, but let's see. Gold is well studied, so let's look at molecular dynamics of gold crystal. Basically, if we look at a gold crystal, what's going to happen is it's going to, this is freezing. We'll just look at freezing gold here. It's a gold nanoparticle, so this is small, tiny crystal of gold. In the liquid state, there's going to be translational motion. So this is at 940 kelvin, it's a liquid state. So the gold atoms can translate. Then we're going to cool it down. They're just moving slower and slower as we cool it down. So less and less kinetic energy. And then when it freezes, we form bonds. We're going to form a metallic bonds when it freezes. So when this hits the freezing point of gold, I wanted to go the opposite way, but it's okay. We'll go from liquid to solid. And so when we melt something, we got to break those bonds. When we freeze it, we form the bonds. So I should speed this up. Now it's frozen. Do you see the translational motion stop? Now what we do is when we cool this down, we're not forming anything. We're just slowing it down. So when the object warms or cools, you just speed up the motion of the particles. But when we actually melt it or freeze it, we form or we break bonds. When we freeze it, we form the bonds. When we melt it, we break the bonds. So all the energy is used in that process there. And so all those are going to be related, what kind of bonds are forming here and there. And so that's why I wanted to just do a quick review of these. If we're, we have different types of attractions between the particles. What types of things hold particles together? And so forces between particles. So for example, gold has metallic bonds, forming metallic bonds. Salts have ionic bonds. And things like quartz or silica, those would have covalent bonds. And so metallic bonds would be like gold, solid AU. Ionic bonds would be solid sodium chloride. And covalent bonds, give me an example of a solid then. Covalent would be SiO2, quartz, solid. The forces between the particles. These are bonds, so these are very strong chemical bonds. And then we have intermolecular forces. We have intermolecular forces. In the video, the guy was talking about intra versus inter. Intra, have you heard that? Intramolecular. Intramolecular means within. It doesn't have to be a molecule. These form lattices. Inter means between molecules. And so as far as intermolecular forces, we have the H bonds. H bonds aren't real bonds. H bonds are just a dipole, unusually strong dipole, These unusually strong dipoles happen when hydrogen's bonded to what? 3 elements?
Fluorine, oxygen, nitrogen.
Yeah, fluorine, oxygen, or nitrogen. These are big dipoles. And then as far as we have normal dipoles, which is called dipole attractions. This is a case where hydrogen may not be bonded to something like fluorine, oxygen, or nitrogen. Let's say hydrogen is bonded to something like chlorine. Chlorine's no slouch, so we'll still have a dipole, but it's not unusually strong. It would just be a normal dipole. So it's something like HCl would be like dipole. And then we have dispersion, or London dispersion, or what else was that called? It's called dispersion, London dispersion, or instantaneous, and one more word, begins with an I, instantaneous induced dipole. So those are all classified as dispersion. So dispersion happens between all molecules. Happens between all polar and non-polar. Non-polar and polar. Happens between all non-polar and polar, but are the sole IMF. IMF stands for intermolecular force for non-polar. example, helium, the only force of attraction is dispersion. So dispersion is often thought of as kind of weak, but it need not be so weak compared to H bonding. So for similar small molecules, H bonds are the strongest, followed by dipole, followed by dispersion. For large molecules, dispersion can be significant. But for because large molecules are quite, what was that word? If I have a large molecule, I have a big electron cloud. If I have a big electron cloud, that's much more, what was that word? P, started with a P. Big electron clouds are much more easy to distort. Easy to distort means starts with a P.
Was it polarizable?
Yeah, much more polarizable. So for large molecules, dispersion can be quite strong. Most significant. Or actually is significant. But typically, H bonds are the strongest because those have the biggest dipole, followed by dispersion. Dispersions, the dipoles are temporary, they call it. So it's not a permanent dipole. And so what we see is that what holds the particles together in liquids are intermolecular forces. In liquids, because in a liquid there's translational motion, right? So liquids. So we're going to just look at liquids for right now. Liquids, we have translational motion. So the IMFs hold the particles together. Not like, for example, liquid gold. It's kind of the IMFs, the dispersion forces between the gold atoms holding them together. Not the metallic bonds, because the metallic bonds would freeze it. So IMFs hold liquid particles together. And so this is basically what you need to know. The stronger the IMF, then the boiling point, the higher the boiling point or the lower the boiling point? The stronger the IMF, the higher the boiling point or the lower the boiling point?
Higher.
The higher the boiling point. So it's going to boil at a higher temperature. It's going to require more heat to vaporize it. Okay, what other properties did we look at? We looked at heat of vaporization. The stronger the IMFs, the bigger or the smaller the heat of vaporization? So is it going to require more heat to boil it or break it apart, or less heat with the stronger IMFs?
Probably more.
More heat. Great. What else did we look at? We looked at surface tension, we looked at viscosity. Let's talk about viscosity. The stronger the IMFs, viscosity is like the glue, how sticky the particles are. There's a lot of sticky. The particles are really sticky, then does it flow easily or it doesn't flow so easily? So the particles are getting stuck to each other, it's more viscous. And so the stronger the IMFs, the higher the viscosity or the lower the viscosity? The higher the viscosity. The higher the viscosity, the more syrup-like it is. The lower the viscosity, the more water-like it is, let's say, or ethanol-like, easier to flow. Then we had surface tension. What happens with surface tension? The stronger the IMFs, the greater the surface tension or the lower the surface tension? That is, surface tension is you gotta break the surface. You break the surface, the higher the surface tension. It's gonna require more energy to break the surface. And then we had something else. It's called P-VAP, or vapor pressure. Vapor pressure. stronger the IMS, the higher the vapor pressure or the lower the vapor pressure? The vapor pressure is its tendency to evaporate. Things with a high vapor pressure evaporate easily. Things with a low vapor pressure don't evaporate easily.
So it's part of low.
Yeah. It's lower the vapor pressure. It doesn't evaporate very easily, so it's not going to cause much vapor. We didn't get into recognizing that much. Let's just look at these three here right now. These are the vapor pressures. This is very weird because the higher the vapor pressure, okay, which one of these has the highest vapor pressure? Diethyl ether, ethanol, or water? You think water has because it's for this. But what you have to do is you pick a temperature. Let's pick 40 degrees C. What's the vapor pressure of water? Water has a vapor pressure here, 40 degrees C. What's the vapor pressure of ethanol? Ethanol has a vapor pressure here. What's the vapor pressure of diethyl ether? It's way up here. And so the species with the highest vapor pressure would be diethyl ether. Well, that means diethyl ether must have the weakest IMFs, weakest intermolecular forces. And so what are the weak intermolecular forces here? Well, when we're looking at this, the gray and the white, these are called hydrocarbons. When we look at hydrocarbons are non-polar, so it's only dispersion. And then we'll see polar. This is going to be a polar bond here. And so here's a polar bond here. And so we see dispersion and we see dipole. Dipole is, we have a carbon-oxygen, so it's going to make a dipole like this. Here we're going to have a dipole here. Here we have carbon-oxygen, so it's the same. But here we have an oxygen-hydrogen. If we have a hydrogen-oxygen link, that's called hydrogen bonding. This hydrogen bonding is very strong as far as dipoles. So here we just have a regular dipole. Here we're going to have an unusually strong dipole. It means it's going to have stronger IMF. Here we have two hydrogen-oxygen links, so we have twice as much opportunity for hydrogen bonding in this versus this. So this is going to be the strongest. If we look at ether, this is diethyl ether. If we look at something like, what is this, 1, 2, 3, 4? If we look at something like pentane, it would have much higher vapor pressure because pentanes are called non-polar, so we only have dispersion. Maybe it has. I got to look at it. So those are starting to get bigger. All right, this is chapter 15. That was a little summary I wanted to do with liquids. So organized. It was just random properties presented. So what do we have next? There's a lot of chapters. So chapter 16 is next with solutions. Let's take a look at solutions. Solutions are, we'll just say, we'll look at some problems from chapter 15 as well. We'll look at those as time goes on. Solutions are homogeneous mixtures. Homogeneous mixtures, it's uniform. It looks uniform. Solutions, we could have gaseous solutions. Air would be a gaseous solution. Air looks totally homogeneous. It does not look heterogeneous. It looks uniform. Drinking water, drinking water looks homogeneous. That would be a liquid solution. A solid solution would be something like brass. Brass is not a pure element. Brass is a mixture. But it looks uniform. It looks homogeneous. So brass could be mistaken for an element. Well, the other stuff's not important. Let's skip the others. When we look at solutions, we have a major component and a minor component. The minor component is called the solute, and the major component is called the solvent. And so the solute are the solids or gases dissolved in liquids present in relatively small amounts. Solvent is like, so for example, if we're looking at sugar water, sugar would be the solute, and water would be the solvent, sugar water. Here they're going to make a solution. The solute that they're going to use, this looks like copper sulfate. To me, copper 2 sulfate. That structure is not copper 2 sulfate. It doesn't matter. They take some salt. The salt is soluble. So they take the salt and dissolve it. So this will be the solute. This is solvent. So let's just take some of this, dissolve it in the water, try to crush up all the crystals. Not all of it's dissolved. I see some crystals down here, but eventually those will probably dissolve. Look at this. So it's mostly water, which is the solvent, and then we have the solute. Since this is a soluble salt, it breaks up into ions. We have the copper 2s, and then we have the minus. This is probably copper 2 chloride. It's like, then it makes sense. If this is copper 2 chloride, copper 2 ions here, these would be chloride. We can make the solutions concentrated, or we can make them dilute. Concentrated means lots of solute. Dilute means very little solute. So concentrated sugar water versus dilute sugar water. They put some copper wire and dilute silver nitrate. There's a reaction there. Let's take a look at that reaction here since we're doing our review. Chemical reactions. Let's figure out what reactions take place there. So what's the formula for copper wire? C is solid. What's the formula for dilute silver nitrate dissolved in water? AgNO3 AQ. I guess we'll leave the AQ off. What type of reaction is this? This looks like a single replacement reaction, doesn't it? Except it's nitrate. We got to worry about nitrate because what do you know about nitrate? Nitrate is a strong oxidizer. So let's take a look at our chart here. Let's see. We have two strong oxidizers here because we have silver ions and we have nitrate ions in solution. So silver ions are a strong oxidizer and nitrate ion is a strong oxidizer. But, well, which one's stronger? Because the stronger one is the one that's most likely to react. So which of those is stronger? Silver or nitrate? Nitrate's stronger. Nitrate's closer to fluorine. However, I don't know if this was effective. Does anybody remember this? It's missing a key ingredient. What analogy did I use? So for nitrate to work properly, we need 1 cup of nitrate, which would be like sugar, and 4 cups of H plus would be like flour. So if you're going to make some cookies, you have 1 cup of sugar, 4 cups of flour. Well, if you don't have 4 cups of flour, can you just make the cookies out of 1 cup of sugar? No. So that was the analogy I used, but maybe you should reframe that in your own words. And so, unfortunately, yeah, nitrate is more powerful, but we're missing the key ingredient. What ingredient are we missing? Hydrogen ion. And so we need, like, if we add HCl to this, yeah, then no problem. If we add some acid, we just need some acid. If we add acid to this, that would supply H+. Do we have any acid? We don't have any acid. And so what that's going to do is, we're missing this ingredient, so we have to eliminate this as a possibility. And so the strongest oxidizer will be silver ion. And so what happens is the single replacement method works. The single replacement method always assumes B is the oxidizer, A plus BX, where B is the oxidizer. Well, that's okay because silver ions will be the stronger oxidizer. And so A plus BX yields AX, copper. Is it copper 1 nitrate or copper 2 nitrate that we should make? Copper 2. I mean, when we look at this chart, do you ever see copper go to copper 1? No, I only see copper go to copper 2. So therefore, I'm going to just take it to copper 2 nitrate. Copper 2 nitrate has what formula? Nitrate salts are all soluble, so that's not going to precipitate. Okay, so I'm going to get AX plus B. B is just going to be silver. Silver alone is silver metal. And then we take a look this, you know, as far as activity series go. Which one's more active, silver or copper? Silver's here, copper's here. Which one's more active, silver or copper? Copper's more active. So we're going from more active, a better reducing agent. So we're going from stronger reducing agent to less active. Less active means weaker reducer. So the driving force is going from a stronger reducer to a weaker reducer. And therefore, we expect reaction. So let's go ahead and balance it. We'll need 2 silver nitrates. And that'll give us 2 silvers here. Just balance. So it turns out that the nitrate's going to be a spectator. That's because nitrate has to be a spectator in this case because there's no H+. And so this is called the CE. For single replacements, we do the CE and the IE and the NIE. And so the IE is going to be copper. Now, copper, do we ionize it? That's a metal. Silver nitrate, do we ionize it? Yes. What does it ionize to?
Silver ions.
Silver ions and nitrate. Is that correct?
You gotta put 2 in front of them.
Yeah, a 2. It's a common error. People don't put 2. Okay, copper 2 nitrate. Do we ionize it?
Yes.
Yes. It's going to go to copper 2 plus how many nitrates?
2.
Silver metal. Do we ionize it?
Leave it on.
Leave it alone.
You gotta still put 2.
Yeah, I got the 2. This is not balanced. All right, then, yeah, nitrate wants to react, but it can't because we're missing the H+. So nitrate's going to drop out as a spectator, unfortunately. If there was H+ present from any source, then nitrate wouldn't be the spectator. Nitrate would be the strongest oxidizer present. And the strongest oxidizer will react with the strongest reducer present. In this case, since the H+ are missing, the next strongest would be silver ion. So that would be it. Nitrate's a spectator. And a flip. So this should be the reaction. The silver ions oxidize the copper to form copper 2 ions and silver metal. So this is what we're seeing in the beaker. What's happening here is that the the copper, you can't even see the copper because the silver's depositing on top of the copper. So the copper's being eaten away, and we see silver metal coating it. Yeah. Take a look at the color of the solution. The color of the solution is turning blue. The blue color results from copper 2 ions. Copper 2 ions have a blue color to them. This is in dilute after several hours. The light blue color is because it's dilute. As the copper 2 becomes more and more concentrated, the color deepens. Take a look at these silver. Silver forms these needles. These are like stalactites or stalagmites, or whatever they call them, on the ceiling, I forgot. But anyway, you can see it. It's pretty neat. So this is after several weeks here.
We're out of time.
Okay, we'll stop. Okay, so we'll continue this next.